Welcome to the course. After the midterm, I hope you all did well with the midterm. Today, first I want to pause for a couple of seconds to pay our respect to the Ukrainians who are fighting for their freedom and for our freedom. And today I want to finish the Flavius Josephus problem we started last time. Last time we saw an active object version of this. And now I want to show you deterministic data flow version and compare the two. They're very different paradigms, and it's very interesting to compare how the same protocol looks in both of them, to give you an idea, okay? So I recall the story. We have n victims in a circle, numbered from 1 to n, and every kth victim disappears, and we keep circling until there's only one left. And the problem is to find the number of the survivor, the last survivor. Last time we defined a protocol for this, a multi-agent protocol, where each victim is an agent receiving messages and sending messages, okay, in a ring. Okay, very good. And now we're going to go to the thing that I want to really show. I'm going to show you very briefly again the active object implementation, and then we will make a deterministic data flow implementation, which is very different and actually much smaller. You'll see how to compare. So this one is something everybody knows, object-oriented programming, active objects, which you can use in concurrent setting very nicely. So the protocol is very intuitive here. But this way of doing things is different. Okay, you have streams, stream object. This is the pure declarative way of doing things. And so protocols are defined in a slightly different way, and you'll see how it works. Okay? Okay, so let me first refresh and put in the active object, and then we'll go to the deterministic data flow. So let me, again, very briefly show you the active object. So I have to define the abstraction that creates active objects first, which I will do. So this is the abstraction. Remember, this is a very nice abstraction. It combines three ideas here: an object, a port, and a thread. And you can see that we're reading all the messages in sequence, and this for statement is doing synchronization. Whenever a new message appears in the stream, we will execute the object. So this is a concurrent program, okay? It's not the same as a sequential. This stream is potentially unbounded. So this thing will keep accepting messages, and the output is actually a one-argument procedure to make it look like an object. Okay, so that's just to make it look like an object. So I compile this. So this has been compiled. And now I can define the Flavius Josephus. So first I'll show you the simple protocol. So this will refresh your memory. Yeah? I'm going to very briefly just execute it again, and then we'll go to the deterministic data flow version. Here I define a class with attributes and methods. The attributes, there's an identity, so the number of the victim, a Boolean alive. This is the K is the number of messages, the number of steps you take for killing, the variable of the last survivor, and successor gives me a reference to the next victim in the ring. Okay, and I have two methods. So a set successor, this is for initialization, and a kill method. So this method is the heart. Defines the protocol as we define it all the different cases. If the victim is alive. If S is 1, then it's the last survivor, and I'm done. I bind last to my identity. Otherwise, I check whether I have to kill myself. X mod step is 0. And otherwise, I just pass the message. Notice in these two cases, I'm passing a kill message to the successor, either with S or S minus 1. Okay? And in the case that the node is dead, it just passes the message to the successor. In one previous course, clever student said, well, in the case it's dead, the victim is like a zombie, which does something, but it's still dead, okay? So it's just passing the same message. So that's the victim class. And we'll run it. Okay. Here, feed region. Good, it's accepted. And now the initialization of the Josephus of the ring, the creation of the ring and starting the program. Okay, so this is the function Josephus nk. I'm using an Oz data structure called an array, so I'm not going to go so much in detail except that it allows me to index. It's an index data structure, so it kind of simplifies building a ring. So I first make n objects here for I in 1 to n. I create using the new active. I now connect them into a ring. And now I have to do a little bit a trick, because from 1 to n minus 1 it's easier. I have to set the successor to I plus 1. But for the last one in the ring, I have to set the successor to 1. Okay, so I have a little thing here. And then finally, to start the whole business, I insert a kill message to A.1. And then it runs, and I return last. So this thing will be running, it's a concurrent program, and eventually the last will be bound. Okay. So that's all refresher. We saw that last time. Sorry, freed region. So this is accepted, and now we can run this thing. 40 guys in a circle, 3, every third man must die, and number 28 is the survivor, okay? But of course you could run it for much bigger than that. If I have 10,000 guys in a circle, every 100th guy, that's much harder to do in real life. Notice it's unbound here, because it's actually running. It's running out, eventually it gets there. So it's doing a lot of work. Well, this guy will create 10,000 victims, which is 10,000 threads. And each step, you have to pass over 100 victims to get rid of the next guy, okay? And the more dead ones you have, the dead ones don't count. So at the very end, when most of them are dead, you're going to be passing over many victims, hundreds, thousands, before finding a new alive one, okay? So at the end, this is actually doing lots, going around very often in this ring of 10,000 threads. So you can see it takes some time. You can actually optimize that by removing the dead victims from the ring. That's what I call the short circuit protocol. So I'll show you how to do that. It makes it a lot faster. But now let's go to the deterministic data flow version. Okay. Okay. So the deterministic data flow version, let me first make a picture of how this thing should work. Here. And then we'll look at the code. So the victim I, has an input stream, which I call IS, and an output stream, JS. And the messages appear here. So there's a kill message, for example, XS appears here, and then the output one can be something like this, or whatever. So the victim receives these kill messages in a stream and has a case statement, okay? And now we have to make a ring So the victims are basically connected in a ring. 1, 2, 3, n minus 1, n. Going around like this. And how do we construct the ring? Well, we construct the ring by first making a pipeline from 1, 2 to n. And then we connect the end to the beginning. Okay, so it's a different way, but it's still going to be a ring here. But these are all streams going around. Okay, so how does it look like in code, in the code? Okay. So let me show you now the code of this. Well, first I have a helper function called pipe, which creates the pipeline. Okay, it creates a pipeline going from L to H, low to high, 1 to n, but from any number to any number, with an input stream xs. And the result of the pipe function is the output stream. So this is a recursive function. So how does it work? So it basically works like this. To create a stream going from L to H, this is the pipe function. It's basically going to be working recursively, yeah? So I have this recursive call here. So this is pipe from L to H. This one will go from L plus 1 to H. The output stream, input stream. Okay? So this is basically just a recursive function. You see how it works, huh? It's not so complicated. It's very simple. So if L is less than or equal to H, I will create a victim. So the function f is creating a victim. And this is then input to the recursive call. Okay? So that's pipe. So that's my helper function. And here's the Josephus function. And here's the victim. So this victim function corresponds to the class in the active object version. This victim function takes an input stream and returns an output stream. It also has an identity. The identity is just the second argument, which doesn't change. Okay? I, which is the number of the victim. So now we have a case statement, but reading messages from the stream, kill XS message, and now we have the protocol. So here is the protocol. This corresponds very closely to the protocol for the active object. If S is 1, then last is I. So last is a global unbound variable, and nil is returned. Nil means the stream is done, it's finished. Okay, so this guy will actually clean up the ring. At the very end, the ring will disappear here. The ring will completely disappear. If x mod k is 0, then the output is kill x plus 1, s minus 1, followed by xr. But there's no recursive call. And here, if x mod k is different from 0, then the output is x plus 1s. So I go to the next guy, but I don't kill myself, and I do a recursive call. Notice the difference between these two here. The recursive call means that the victim is still alive. Okay, in a sense, I'm recreating the victim, okay? The victim is still alive here. Whereas in this case, I'm not doing a recursive call. I'm passing the input stream, XR to the output. So in this case, the victim is dead. You see the difference? So the way to keep the victim alive is to either do a recursive call or not. Okay? And that's it. That's the whole protocol. And here I build the pipe. So basically I build from 1 to n. Here I have a function. So this is the function f, which is creating the pipe, which has the input stream as an argument and the name, the identity, the number of the victim. So is, okay, which is the input stream here. And this function will create a new victim here inside its own thread. So this is a nice example of higher order programming. See how it works, huh? So it's nice to look at what the contextual environment would be of this function, since it's referring to victim, okay, which is defined there, okay. Also, the victim function is binding last, which is defined here. So that's part of its contextual environment. You see how functional programming makes it really nice structure. And so it's in a thread, and the result of this call will be the output stream. Okay? So the pipe will create from 1 to n, but then we have to connect the output to the input. So ZS is the output of the pipe at the very end. We have to connect it back to the input, ZS. But I stick in a kill message before. This is like the first message in the active object to make it run. So kill 1n bar ZS. That means there's always a kill message before ZS. Okay? But ZS here will connect the input to the output. So this instruction here creates the whole ring. Okay? So it's very concise. In fact, the length of this code is very concise. And it also automatically removes dead victims from the ring. So the ring gets very shorter and shorter. Okay? What happened here? Oh, wonderful. Thank you, Doctor. Why did it disappear? We'll have to restart it. Ah, there it is again. I'm not sure what's the problem with Docker, but I will have to re-put in the code again. Okay, let me put in all this code. Okay. So I compile this one. This one, region, and now I can run this beast. Okay, Josephus 43. Sorry, it's not called Josephus. It's Josephus number 3. Okay, Josephus 3. Okay, so let me run it. And it gives me 28. So that's good, huh? But let me run the other one now, the one that I did in the previous example. So we want to compare the two. The previous one I did 10,100, okay? It's actually much faster. You see, it only paused an instant. But here again, I'm creating 10,000 threads, and I'm circling. But this one is actually smarter than the active object. This code is actually smarter because when the victim dies, it's automatically removed from the ring. Okay, it's very easy to do here. So the active object one doesn't do that, so it's less efficient. That's kind of a pain. So what I want to do now is make the active object one as smart as this one. Okay, I want the active object code also to remove the dead victims. Okay, you see how it's working, huh? You get the idea. Okay, so let me make a picture here. This means that the active object code will get a little bit more complicated. It's kind of a machine language, huh? So here's in the active object version. Okay, I have the ring. Let me just draw a piece of the ring here. Now assume this guy dies. And these are successor pointers, huh? Each object points to the successor. Now assume I kill this guy. I want to repair the ring. I want to remove it from the ring. Basically, I have to change this successor pointer to point to that one. How do I do that? Well, it means I have to do some administration, some bookkeeping here, some plumbing. So how do I do that? Well, I'm here, okay? This is the object I'm running, and I need to change this guy. Means I have to send a message from this one. Let's say this one is I minus 1, I plus 1. I have to send a message from I to I minus 1. It means I need a predecessor pointer. This one has to know the predecessor because it has to change this pointer, this successor pointer, okay? That means all objects need a predecessor pointer now. That's a little bit more than before. Also, I have to also update the predecessor pointer. It's not enough to update the successor pointer. It means this predecessor pointer of I plus 1, I have to change it also. So that means this object has to send a message to the predecessor and to the successor to update the successor pointer and to update the predecessor pointer, okay? So you have to do 2 extra operations to fix the ring, to remove this guy. You see that? Okay, so let's do that. So let me just show you the code that does that. Okay, this is the one using the short circuit version, which I call the short circuit version. Okay. It's a little bit longer than before. So this is the new version of the active object. Now it has a successor and predecessor pointer. Okay, it has 2 extra methods, set successor and set predecessor. And now when the node dies, so most of it's the same, but when the victim dies, alive gets false, I have to fix the ring. I want to remove the node from the ring, so I send a message to the predecessor to give it a new successor. So the new successor of I minus 1, the new successor of I minus 1 is actually the successor of I. It's this one, which is the successor of I. So that means the predecessor, I send the message, set successor, and my successor. It's I that's executing this. You see that? See what I'm doing here? And I have to do the same in the other direction. To the successor, I have to set predecessor. And the predecessor, the new predecessor, is the predecessor of victim I. Here. So I have to send these 2 messages, and then I do the kill. Okay, and now I'm done, right? Well, not quite. I'm not quite done. And the reason is, this is a concurrency problem here. When this kill message is now going in the ring, x plus 1, s minus 1, it's going in the ring, and it's going all the way around. Eventually, it will make its way back. So the kill message here goes in the ring, and goes all the way. Eventually it makes its way back here, but it should see a fixed ring. It should not see a half-fixed ring. Both of these pointers, successor and predecessor, have to be correct when the kill message comes back here. So we have to prove that. I've put 3 messages in here, in the ring. And this is concurrent. This is a concurrent system. So all of these messages are basically traveling asynchronously, right? So we have to show, or we have to make sure that this kill message, when it comes all the way back, that it sees a fixed ring. That means that the 2 messages here have been treated. How can I prove that? Okay, we have to prove that. The comment gives you a hint. It actually is true. When you can actually prove that when this kill message comes back, these 2 will already be done. And the reason is because of FIFO property. And the FIFO is, I can prove it as follows. When I send a message to a port, When I send two messages to a port from the same thread, the first message I send will be arriving first. So the order of the sends is the same as the order of the receives. You see that? Because each time I do a send, I add it to the stream. And so it has a position in there. So you can actually prove now that the ring will be fixed. Do you see how to do it? You want me to do it for you? Not so simple, huh? You have to think concurrently. Okay, here's how to prove it. Assume I look first at this one, I minus 1. Okay, there's two messages going to I minus 1. There's this one, the set successor, and then there's the kill message eventually when it comes back. Okay, so there's going to be two messages. Which one is first? Which one will arrive first to I minus 1? The set successor or the kill? And why? Now I'm asking you guys. So basically, this is the question, If you look at I minus 1 here, there's going to be two messages coming here. The set successor and the kill when it comes all the way back. Which one will arrive first? What do you think? Which will arrive first? You tell me. You see what I'm doing here, I'm looking at I minus 1 and I'm looking at the order of message arrival. Which of those two will arrive first? And can you prove it? Well, what is the order of send? What is the order of the sends? Well, this set successor was sent before the kill. And this kill, it's not the one that's going to arrive at I minus 1. Because this kill will go through a bunch of victims and there will be another kill. So later on, there will be another kill. Which means the set successor is sent first. You see that? Because of FIFO, it will arrive first. You see that? Simple, right? Right? Is it simple? So the set successor, what is this stupid... Okay, so there's a problem. This Docker is a pain, okay? Docker is a pain. Okay. Why does it... There is something going on, it must be an internet thing. Let me change the network, you see the name. It must be something like a keep alive, so let me put it in again. Okay. So why is it not? Oh, Docker is such a great thing, huh? Oh, wonderful. What a great piece of software, huh? Okay, so easy to use, reliable. Okay, so here, so we know the set successor will arrive before the kill, and that means once the kill arrives, the ring, this node will be repaired. It will have a correct successor. So we're good. The predecessor also is correct. And the same thing, same reasoning we can do here. The successor is correct, so it will come here. But here also there's two messages coming to the I plus 1. And because of FIFO, but here it's a little bit more subtle. I'm directly sending them to the same node. Successor this, successor this. But because I send the set pred before the kill, the set pred will arrive before, and it will fix the I plus 1, and when the kill arrives, it will see a nice thing. So the kill never sees the plumbing that we're doing. It sees only a correct reading. Okay? So this is good, huh? Okay. Now let me run this guy. Okay. Well, first I have to this. have to define new active again. Variable new active, of course, I have to define this one first, the abstraction. Okay. Paste. Okay. This one. Now good. Now let me just do this one. This one is called Josephus 2. Let me do 43 just to verify that everything is working. This gives me 28. Now let me do Josephus 2, 10,100. Ah, you see it's much faster than before, huh? So the short circuit protocol actually succeeded in making it go a lot faster. So here's the code for the short circuit. So when I set it up, I have to set up the successors and the predecessors. So when I build the initial ring, I create n victims, I set the successors here, and I also have to set the predecessors. So I have two pieces of code here, and then I stick in the kill message. So this is the initialization, and this is the actual code of it. Okay? So this is nice code, right? Well, if you're using Java, then this is the kind of code you have to write, or even Erlang, you would have to write like this. This is okay, right? You understand it? But let's compare it now to the deterministic dataflow version code. Okay. Notice this one, the active object version, is actually two full screens. Okay. So here is the deterministic dataflow version, the full version. I can scroll it. Yeah, what a pain, huh? And this is in 2022, and they couldn't fix scrolling yet. Okay, so here is the deterministic dataflow version, complete version. And it's doing the short circuit protocol. And I have my little helper function, and I have the protocol itself, and here I'm building it, 2 lines of code. And it's very efficient. They're both, the two programs have similar efficiency. Now, this one, it's only half as many lines of code, actually, as the other one. But it's doing exactly the same thing, okay? So you can see active objects is kind of low level compared to this. This is much higher level in this sense. It's only half as much code. And it's more dense, it's much denser. The pipe is 2 lines. Instead of having all this garbage about predecessor, successor pointers, mutable state and everything, I just have a very simple pipe of streams here. And removing a victim is very easy. Okay? Either I recreate the victim by doing a recursive call, or I just pass the input stream to the output, so there's no more victim. So this is only half the number of lines of code. So it's much denser, and it's even for bigger programs, it's even more the case, okay? Now, this one only works if the code is deterministic, and Flavius Josephus is a deterministic protocol. It's always giving the same result, okay? It's completely deterministic, so you can write it like this. There's no races or anything like that. So, comparing the two, let me now show you some Some slides now. Okay, so comparing the two. So in the active object and deterministic data flow, each soldier, victim, is an active object. Each soldier is a stream object. So here it's a passive object inside a thread, but here it's a list function inside a thread. Here on the left we have a class that defines a kill method that implements the protocol. Here we have a function, victim, that reads kill messages and creates a new stream, depending on the message with the case statement. In the initialization, we have to set the successor and predecessor pointers. Here, we just have to build a ring, so a pipeline when the output is connected to the input. Okay? So you see the correspondence, but in the amount of code, this one on the right is much compacter. Okay? So we can explain a little bit. Okay, so the active object version, the short circuit, we actually have to implement that with a bunch of code. Remove the dead victims from the ring. We have to update the successor pointer and the predecessor pointer of two nodes. And we have to be careful that it's not giving any problems with concurrency, okay? It depends on the FIFO properties. This is important to understand this. The send is as FIFO property. The send order is the same as the receive order. So this you have to be careful. I cannot send, if I change the order that I send the messages, it will be buggy, okay? So it's important. Now the deterministic data flow version automatically, very easily does this optimization. You remove the dead victims by replacing the recursive call by simply the input stream. So there's no more victim, okay? The recursive call is actually a victim. Okay? Doing the recursive call means that the victim is still alive. Not doing the recursive call means there is no more victim. So it's very easy, okay? So you see, semantically, it's a lot denser, okay? So that's a very interesting comparison, huh? I think it's very interesting to compare them, because when you start programming with industrial tools, you will almost always be doing active objects. There are very few tools today, they're coming up, that do deterministic data flow. But it's actually much denser, and it's actually easier to write the deterministic data flow version, okay? Less lines of code, less chance of bugs, and the efficiency is the same. There's no significant difference in efficiency between the two. Okay? So that's the final conclusion of the Flavius Josephus. Interesting, to see the two. So it's important to look at the two implementations and compare them. The paradigms are very different. They look very, very different. And they look quite different, but they're doing exactly the same protocol. Okay? What do you think of that? Okay, so now we go to the next step. Now I want to show you how to write very large multi-agent programs. I'll introduce it today and we'll continue next week. This is used a lot, okay? Program is a bunch of agents that send messages to each other. It's like a whole constellation of agents. And each agent has internal state and they send messages, okay? Now, deterministic data flow is a kind of multi-agent, but a limited kind, only with deterministic behavior. With port objects, or active objects, which is port objects with a class, we can have programs that have non-deterministic behavior. Okay? And so I'm going to show you a big example of this, but for today, I will just give you a simple introduction to that. Okay, we're going to define, so this is what we're going to do next week, a lift control system or an elevator control system. When you go to a hotel, big hotel, usually if you have many lift cages or elevator cages, like 6, and the hotel might have 30 floors, and then there's buttons to call the elevators, and every floor has buttons, and the lifts, they're all going up and down, 6 for example, and they're stopping at the floors, and inside each lift there's also buttons, which floor you want to go to, and you can press multiple of them, you can press them anytime you want. So this is a large concurrent system. You can see it's not so trivial it seems. Every floor has a button outside the floor that you press, calling the lift to go up or down. Every lift inside the lift has a bunch of buttons for the floors you want to go to. And you have n lifts, maybe 6 lifts, and you go up 30 floors. So whenever I go to conferences, I'm always in these big conference hotels, and it's always some big thing like that, okay? Huge number of lift cages, 30 floors, lots of buttons. And they have the human beings using this. They can be at any floor, they can be in any lift, and they can be pressing buttons anytime. And this thing has to work. It's not bad as a concurrent system, huh? What do you think of that? So the usual way to implement that is as a multi-agent system. You cannot have one little Java program sitting here, and each time you press a button, it sends a message. Java comes back. Doesn't really work. Because what happens if the Java program crashes, the whole thing is down, okay? So usually this is multi-agent. The lifts have processors. The floors have a little processor with the buttons, okay? And they can talk to each other. They can send messages to each other. And of course there's the users, which are also have a processor in their head, okay? This is the example I want to show you. And I want to show you a way to do it that makes it correct, using state diagrams, okay? So here's the kind of overview of this thing. So you have lift shafts. Here there's 3, but in a big hotel you can easily have 6 or more. I've been in those hotels. You have n floors, so easily it can be 30 or something. And each of these shafts is controlling a motor. So that's a separate piece, which is either in the basement or it's up on the roof with cables making the lift go up and down. But there's also a control here, a processor here, controlling the movement of the lift. Okay? So you have a lot of components in this system. And then you have the humans, the users. They come to the floor, they press the button, they can also go inside the lifts. Okay? So you have a bunch of components here. So in a big hotel, you can have 6 of these, 6 of these, 30 of those, plus dozens of users, as many as you want, pressing buttons all the time. Okay? And users love to press buttons. You know that, though. So this is a summary of the components and their protocols. Okay? So each lift will be an active object. Each floor will be an active object or port object. We will also model the users. Pressing a button will be modeled as a message sent. Okay? And then there's the controller. So there's a bunch of possible messages here. The user standing in front of the floor calls the lift. The user can be inside the lift wanting to go to floor, so does call F message. The floor, when you do call, it has to actually call a lift, so it sends call F to the lift. When the lift arrives, it sends an arrival, and when the lift is allowed to leave again, the floor acknowledges that it's allowed to leave. And the lift also talks to the controller, because the motor has to start and stop sometime. Whenever the lift wants to move, step message to move up or down, and then when it arrives at a floor, the controller says, you have arrived, so it sends a message back. So you have all these protocols running between these agents, and inside of each of these agents, you have a program. But you have a state here, and whenever I send a message, the state is updated, okay, according to some complicated protocol. And I'll just briefly show you, but we'll go into it next week. So to write this program, we're going to write this program. We have to write the code for the floor, for the lift, and for the controller. All three we have to write the code. And how do you write that code? Well, you start by not writing code. You start by drawing a picture, which is a state diagram. So for example, here's a state diagram of the controller. I won't explain it now. Here's a state diagram of the floor, and here's a state diagram of the lift, which is more complicated. But they're very systematic. You construct them systematically, and once you have the state diagrams, then you can write the code. And then you have this very complicated thing. Notice this is a concurrent, extremely concurrent and non-deterministic system. And you want it to work. A user presses a button, the lift has to come, and it doesn't, and you don't want deadlock or any weird problems happening. Okay? Okay, so that's what we're going to see next time. We're going to see how to do multi-agent programs. And many, many programs in the real world are like this. Okay? They're not like Java program. And they will be using these little microcontrollers and which processors on them sending messages. Okay? But basically it's a multi-agent system. Okay. So let me stop there. And so next time we'll actually be building this system. Okay?